Let's start with Chapter 15, Part 2. And all we're going to do in this section is look at one reaction. It's the Diels-Alder reaction. It's one of the most useful reactions in organic chemistry to form six-membered rings. And we've already talked about in previous chapters how this six-membered ring is important in chemistry and how it keeps coming back over and over and over again. Now, I will preface this by saying whenever I took organic chemistry, and this was back in 1981, probably 1982, whenever I was taking the second semester, I went through this lecture, had the lecture, tried to figure out the reaction, and it made no sense. I did the homeworks. I found the system that kind of helped me get the right answers, but I would hit and miss and sometimes get it right and sometimes get it wrong. And then I started teaching organic chemistry. And again, I could teach it so that students could get the right answer, but I really had no clue what was going on in the reaction. Then one evening after I went home from a night lecture and I taught Diels-Alder reaction, still struggling with it and everything, I went to sleep and I had a dream. And in that dream, I figured out everything there was to know about the Diels-Alder reaction. So it's a very, very simple reaction once you understand exactly what's happening. We'll talk about that in just a little bit. So let's talk about the characteristics of a Diels-Alder reaction. There are 6 of them. And these 6 rules become very, very important. And most of them are self-explanatory. It's a 4+2 cycloaddition, which means 4 carbon atoms react with 2 carbon atoms to form a 6-membered ring. There's going to be a diene involved, okay, and it's going to be a conjugated diene. And it either reacts with an alkene or an alkyne, something that has another double bond in it, and there's where you get your 6 carbon atoms. The conjugated system has 4 carbons, and either the alkene or the alkyne has the other 2 carbons. It's a concerted reaction, and we've used that word before. A concerted reaction is a one-step process. It all happens in a single step. Whenever the reaction occurs, it has to occur so that the diene is in the S-cis conformation. We talked about what S-cis was versus S-trans in the last section. We get something called syn addition, and we've seen that before. They add to the same side. We get syn addition. Now, the only rule that we don't know is the endo rule, and we'll explain what that means later on. So here's what happens in a Diels-Alder reaction. A diene reacts with either an alkene or an alkyne to give a 6-membered ring. There are some stipulations on this. The diene needs to be electron rich. So it needs electron donating groups on it. We'll define what an electron donating group is in a minute. The dienophile, the one that's going to react with the diene, that's either the alkene or the alkyne, needs to have electron withdrawing groups on it. So whenever you're looking at a Diels-Alder reaction, you want the diene to have electron donating groups on it and the other species to have electron withdrawing groups on it. The last stipulation that we need to make is that the electron donating group and the electron withdrawing group need to either be 1,2 or 1,4 on the new ring. They are rarely 1,3. So whenever we get finished, they're going to be 1,2 or 1,4 on the ring, whatever that means. So that's all there is. Okay, so that's everything you need to know about this lecture. Now let's just look at some examples though. I'm going to look at this reaction. And this is going to react with this compound here. Now, this is probably the way this will be given to you on the test. So the first thing that I would do if I were to do this reaction is I would go ahead and put my hydrogens on here. Now, if you want to put the hydrogens back here, you can, okay? And I would put the hydrogens here. Now, let's talk about this reaction and show you what I mean by some of the terminology you've learned before. Notice that this is in the S-cis conformation. Double bond, single bond, double bond, but the double bonds are cis around the single bond. Remember, we talked about that before. So this has to be in the S-cis conformation. Now let's talk about electron donating groups versus electron withdrawing groups. And listen carefully, because a lot of students don't listen to this very carefully and they get confused. An electron donating group, the atom that's attached directly to the double bond, in this case an oxygen, normally has lone pairs on it. Okay, so the electron donating group normally has lone pairs. Okay, an electron withdrawing group, again, we're going to look at the atom that's directly attached to the double bond. So in this case, it's the carbon. It's not the oxygens, it's the carbon. Is either partially charged positive or completely positive. If we look at this carbon, do you agree it's partial positive because it's connected to two oxygens? So if the atom that's attached directly to the double bond is partially positive, it's an electron withdrawing group. And if it's got a lone pair on it, it's an electron donating group. Now, that's not an exact definition, but it's one that'll get us to where we need to be at this moment in time. So notice that our diene has an electron donating group, and our dienophile has two electron withdrawing groups. Now, watch what happens here. This pair of electrons, and it makes no difference which way you rotate these, but I'll try to be consistent with my notes, comes up there. This pair of electrons comes down here, and this pair of electrons moves back there. Now, this is not resonance, this is actually a reaction. So what we end up with out of this reaction is this, a six-membered ring. Now, students oftentimes get lost on this. So you can number these, and it makes no difference how you number them. I'll number 1, 2, 3, 4, 5, 6. And I'm only going to number the atoms that go into the new ring. Remember, we did that last time. So if I do that, then this would be 1, 2, 3, 4, 5, 6. Now, the first thing I noticed that in my new compound, where does the new double bond form at? Between carbons 2 and 3. So I'm going to put a double bond there. Now, notice on carbon 1, I'm going to have an OCH3 group. On carbon 6, I'm going to have this group, and on carbon 5, I'm going to have this group. Now, the question is, are these cis or trans on the ring? And there's a whole bunch of rules you can do for this, but it is really this simple. Okay, and let me get my model here. And I'm going to set this model just the way it looks over here. Notice this is this compound here, and this is this compound. Let me find my double bonds. This is this compound here. Okay, so there are the two compounds. And this is what happened whenever I had my dream. Whenever I had my dream, I was one of these atoms right here in the molecule. So I was seeing it from the molecule's point of view. I mean, it was a vivid dream. I still remember to this day. And what happens in a Diels-Alder reaction is, watch. It's this simple. The two molecules come together and they go poof. So watch. Poof. That's what happens. Or they could also go poof and go down. that just gives you the other enantiomer. So I'm going to always poof up. Now watch, poof. Now, whenever that happens, and I'm going to hold it like this and poof towards you this time. Notice these two hydrogens and these two hydrogens are the ones that do what? Poof. They all stay on the same side. And once I realize that, Diels alder becomes very easy. These four atoms or four groups, whatever they happen to be, are always on the same side of the ring. So notice on carbons 1 and 4, the hydrogens will be on the same side of the ring. So I have the ones that are coming out, okay, that I do not have circled are going to be the ones going back, and the ones that are circled are coming out. So on carbon 1, notice the OCH3 goes back. On carbon 6, notice the C double bond O OCH3 goes back. Notice on carbon 5, this goes back. So all of them are in the same side of the ring. So the stereochemistry on the ring is very easy to see. The four groups that are attached here in the middle all appear on the same side of the ring. And I always have them coming out. Now, I could have had them coming back, but that would have just given me the other enantiomer. Okay, so that's the first thing. Notice these two hydrogens on 2 and 3 are now in the plane of the ring because these carbons are now sp2 hybridized. So that's almost all there is to a Diels-Alder reaction. Realizing that these four atoms are always on the same side of the ring, which means the group that's attached here, the group that's attached here, here, and here are always on the same side of the ring. These two will always be in the plane of the ring. Why? Because that carbon becomes sp2 hybridized. Now, that's all there is to this. Okay? Now, in the next reaction, which is kind of hard to see, we have two 5-membered rings coming together. The first one is acting as the diene, and the second one is acting as the dienophile. The only reason this reaction is on page 2 of the notes is so that I can show you what the endo rule means. Whenever this compound is formed, and in my drawing on page 2, the last drawing I have at the bottom of the page, I left off the double bond between the number 1 and 6 carbons. So go ahead and put that in. But whenever I do this, notice this new ring formed. Whenever you have new rings formed over here, this ring is always tilted in toward the double bond. That's called the endo rule. It's into the double bond. It's not pointed out this way. Okay, so whenever you form new rings in a Diels-Alder reaction, you're always going to form one new ring, but if there's a bicyclic compound formed, the newly formed ring always gets tilted into the double bond. Okay, that's called the endo rule. It's not going to be so important in this course, but again, it is something that comes out of the Diels-Alder reaction. Now, listen carefully. A bunch of questions, okay? A bunch of questions on the test are going to deal with which one of these Diels-Alder reactions will work best. Now, to answer that question, we're going to look at all kinds of scenarios. Some of these scenarios are in your notes. Some of these scenarios are not in the notes. Okay, so you're going to add some of these to your notes that are not in here. The first thing we're going to look at is not in the notes. So you need to add this one to your notes on page 3. I'm going to give you this question on the test. This one's not in your notes. Now listen carefully. The question asks the following. Which one of these two compounds would be most readily useful in a Diels-Alder reaction? Now remember, in a Diels-Alder reaction, the compound has to be in the S-cis conformation. So what you would tell me is this compound is better for a Diels-Alder reaction because it's in the S-cis, where this one is in the S-trans. And you would miss that question on the test, okay? Because this is in the S-cis, and this one is in the S-trans, okay? But it can be placed into the S-cis. So what I want you to do right now in your notes before I do it on the board is I want you to rotate this molecule into the S-cis conformation. So whenever you do that, you're going to have your double bonds like this. I want you to tell me where the methyl groups go. Okay? Now, to answer that question, I'm going to put hydrogens on here. Now, notice what I did with this molecule. I didn't do anything with this half of the molecule. It stayed the same. So my methyls are going to be out here and my hydrogen is going to be there. This hydrogen is going to be back here. But notice what I did with the bottom half of the molecule. I twisted it in. Now, watch what happens. This part of the molecule and this methyl are trans to each other. Do you agree that across this double bond, they are trans to each other? So in this structure, they have to be trans to each other. Since this part of the molecule is going in, would you agree that to make these trans to each other, this methyl has to be going out? So notice this group and the methyl group are trans, so this group and the methyl group have to be trans. So now that we've got this into the S-cis configuration and this into the S-cis configuration, how can we decide which one is better? So if I give you on the test one of them in the S-cis and one of them in the S-trans, the first thing you do is rotate them both so that they get into the S-cis, if possible. Okay? Now, to answer the question now, notice that here, these methyls are blocking this opening. In the Diels-Alder reaction, just like most chemistry reactions, steric hindrance plays a part in it. The more sterically hindered this opening is, the slower the reaction. Notice the two pieces that are inside here. They're two hydrogens. So therefore, this is much less reactive than this because of steric hindrance. So when the large groups are facing in, steric hindrance lessens that reaction. So if I asked you on the test which one of these two would be the better reagent to react with, this one is actually the correct answer because this opening is less sterically hindered. Okay, so that's the first thing. Okay. So now we can go back to the reactions on page 3 that are in your notes. Now we can ask which one of those two reactions is better favored. And notice one of them, the methyl is pointed in, the other, the methyl is pointed out. Notice in this case, both of them are given to you in the S-cis configuration. So obviously the bottom reaction will occur at a faster rate than the top reaction. So if I asked you on the test, the question would read like this: which one of those two reactions would occur more rapidly and why? And you would say the bottom one because the diene is less sterically hindered. Okay? Now, having said that, what else can we say? Let's look at some more examples before we go on over to the other page. And I'll go ahead and write this out for you, C double bond O, OCH3. If I gave you this and said, which one of these is a better reagent in a Diels-Alder reaction? Notice the only difference here is we have this group versus this group. Notice this is an electron with a donating group. This is an electron withdrawing group. And our rule said that the diene should have the electron donating group on it. Now, this is one that students miss all the time on the test whenever it appears on the test questions. I'm going to give you this question and ask you which one reacts faster. Notice both of them have 5 carbons total in the molecule. Okay? Notice both of them have 5 carbons total in the molecule. Which one is going to react faster in a Diels-Alder reaction? Now, if you're formulating an answer in your head right now, you're probably saying this one. And the answer would be why? Because it's less sterically hindered. And in this case, you're wrong. Okay? But you said just a minute ago that anything that points in blocks that opening, slowing down the reaction. This compound actually is very, very reactive, as we'll see in one of the labs that we're going to do in a Diels-Alder reaction. And the reason being is, notice this compound. It's in the S-cis configuration. Now, this one's also in the S-cis configuration. But can it rotate out of the S-cis configuration? Could I draw it in the S-trans configuration? And the answer is yes. So only a certain percentage of the molecules are going to be in the S-cis configuration. Didn't we already say the S-trans configuration is more stable? So only a small percentage of the molecules will be in the S-cis configuration. In this molecule, notice because it's in a ring, it can't rotate. So it's stuck in the S-cis configuration. 100% of the molecules are always in the S-cis configuration. So therefore, it's going to react fastest because it's stuck in the S-cis configuration. Okay? So here's another test question. Which one of these two compounds would be more reactive in a Diels-Alder reaction? Again, you have to be very careful on this one. Notice that this compound is locked in an S-trans configuration. Notice the 2 double bonds are trans around this single bond, where this one is locked in the S-cis configuration. Notice the double bonds are cis around this single bond. So this one would be much more reactive. So I can ask all of those types of questions on the test. So you have to understand what's going on in a Diels-Alder reaction. Now let's go over to page 4. Okay, page 4 brings out really the last little caveat in the Diels-Alder reaction. In a Diels-Alder reaction, now listen carefully, and this will make perfect sense. In a Diels-Alder reaction, what's the product of this reaction? Now listen carefully. If I look at this diene, do you agree the top is different from the bottom? So we say that is an unsymmetrical diene. the group attached to the top is different than the group attached to the bottom. This is the dienophile, the thing that's reacting with the diene, in this case an alkene. Is the top different from the bottom? Remember, there's an H attached here. And again, if you want to put your H's on there, you can. Now listen carefully, because you're going to miss this on a test. If the diene is unsymmetrical and the diene is unsymmetrical, or the dienophile is unsymmetrical, there are two possible ways these can combine. We can combine them just like we wrote them, or I can flip one of these over, and I always choose to flip the dienophile over. Do you agree that these could react in both of these methods? Here the two groups are on next to each other, here they're far apart. Now, once we do that, and again, I can put my hydrogens on here so that I can keep everything straight. Remember, the reason for putting the hydrogens on there is that notice these four atoms always go on the same side of the ring. So that whenever I draw the product, now notice I'm just going to draw my six-membered ring. Again, if you want to number these, you can. Again, remember the double bonds move if we want to think of how to keep track of the electrons. So here's going to be my new double bond. Notice that this atom is this atom, so the OCH3 goes back. Remember, these four atoms are the ones that come out. And again, you could do this the other way. I just choose to do it that way. So this also goes back. Now notice the other combination. The double bond again is formed. There's my OCH3. And notice in this case, my C double bond O OCH3 goes here. Okay, does everybody see what I did? I just flipped this over and wrote my two combinations. Now, if we go back to our 6 rules that we had on page 1 of this, the last paragraph on that page said, when you have a choice, you want the electron donating group on the dienophile and the electron withdrawing, on the diene, and the electron withdrawing group on the dienophile to be either 1,2 or 1,4, but not 1,3. And notice they're 1, 2 to each other. Over here, they're 1, 2, 3 to each other. So this will not form. This will be the product that you get. And again, I don't have to give it to you in the correct orientation on the test. So if I give you one like this where the diene is unsymmetrical and the dienophile is unsymmetrical, what you're going to do is write both possibilities out on your scratch paper and then decide which one of them is the correct one. Okay? And you want to keep those two groups 1, 2 or 1, 4. Now listen carefully. Something else that is not on your notes that you're going to add to the bottom of page 5. It says, what's the major product of this reaction? Now, I'm going to put both of these on the board. On this one, we've got an OCH3 here and a CH3 here. So do we agree this is an unsymmetrical alkene? Okay, do we agree that's an unsymmetrical diene? Then we're going to use our other one, which is this. Do you agree it's also unsymmetrical? Okay, so we've got two of these that are unsymmetrical. So again, we have to go through both choices. Now, the easiest way for me to do this is just to flip this one over here. So I'm going to write it like this. So everybody see what I've done? I've just turned it over. Now let's go through our two combinations of our products. So here's going to be my 6-membered ring. Notice in this case, again, the double bonds move. So I'm going to get a double bond here with a CH3 here and an OCH3 here. Now notice as I showed those CH3s and OCH3s, I did not show them going behind the board. I did not show them coming out of the board. They're in the plane of the board because these carbons are sp2 hybridized. You will lose a point on the test if you don't do that. Now on this one, notice this goes back. The product down here would be the same thing. The OCH3 is here, the CH3 is here, but notice down here, the double bond OH is there. Now the question is, which one of these are formed? Notice we have two groups attached to the dienophile. Both of those are electron donating groups. One is a better electron donating group. The methyl group donates electrons via the inductive effect. You know, it just donates electron density down. The OCH3, as we're going to see in just a second, donates via resonance. And what have we always said? If resonance is in the picture, it wins. So the stronger electron donating group is the OCH3. So the OCH3 and the C double bond OH are the two groups that we want to be either 1,2 or 1,4. We don't have to worry about the methyl. So whenever I number these, watch this. This would be 1, 2, 3. Notice the OCH3 and the C double bond OH are 1, 3. Notice in this case, 1, 2, 3, 4. Notice they are 1, 4 to each other. So this is the correct answer. Okay, this is the correct answer. So on the test, if I gave you this, this is the answer I'm looking for. Now, what do I mean that the OCH3 can donate via resonance? Why does that rule work? Why does the rule work that the two groups want to be 1, 2 or 1, 4 and not 1, 3? Now, let's show that by resonance, and I want you to add this to the bottom of page 5 in your notes. So this is the correct answer that I want. So I'm going to go ahead and get rid of this problem now. And I want you to look at something and understand this via resonance. If I just, let's make the problem simple again. And we're going to compare this to and react it with this. Now, if I put lone pairs on that oxygen, and I'm going to go ahead and put my hydrogens in here. Now, watch what I can do. Suppose I gave you this on a test, just that question, this formula. Can you draw a resonance structure for that? Watch what you can draw. You can move this pair of electrons down, this pair of electrons down, and this pair of electrons over. So if I were to draw a resonance structure for this, I could draw this resonance structure. Let's see, the double bond there, the double bond there, and this CH2 now has a lone pair on it. Now, if I were to ask you on the on test 1 of last semester, is this a good resonance structure? You would have probably said no. Notice we have a lot of charge separation. We've got negative and we've got positive. We've got a positive charge on oxygen. So this is not a great resonance structure, but it is a resonance structure. Okay? Now, if I'm going to do the same thing for this structure and draw a resonance structure, now notice what we now mean by electron donating. This pair of electrons was donated down into the ring. If I'm going to draw this and I'm going to put the CH2 out on there, the electron pairs move in this direction. Notice what I mean by electron withdrawing. They're pulling electrons away from the ring. So I can now draw the following resonance structure. And I'll put my H out here. Let's see. So there's that, hooked to that carbon, and this oxygen, which now has 3 lone pairs on it. Notice this oxygen is negative and this carbon is positive. So based upon these resonance structures, notice whenever things react, opposites attract. We've said that several times before. Notice this end lines up with this end because this negative lines up with this positive lines up with this negative. So this molecule is not going to turn itself over because then the positives and the negatives would be on the same side. So because of these resonance structures, it forces the molecule into this orientation so that it will react to give us only the 1,2 or the 1,4. The 1,3 product would require the positives and negatives to be close to each other. That's all we're saying. So resonance explains why the 1,3 rule does not work and the 1,2 and 1,4 rule does work. Now, we're going to all we're going to do for the next 10 or 15 minutes is I'm going to give you some more reactions. So before we go over to page 6, on the test, you're going to have the following reactions, okay? I'm going to give you a Diels-Alder reaction, and I'm probably going to give you one of each one of these. I'm going to give you the reactants, and you're going to predict the product. Then I'm going to give you the product, and you're going to predict the reactants. Okay, so let's look at both of those. So here's a question on the test. This would be a typical test question for a Diels-Alder reaction. Predict the product of that reaction. That's all there is to it. And here's what you're going to do. Now again, if you want to, you can put your hydrogens on here. I recommend doing that while you're learning this because it's easy to keep track of what goes out and what goes back. These 4 go out. So watch the product. Notice the double bond comes back here, so the OCH3 is going to be in the plane of the board. This group is going to be back. And congratulations, you've completed the Diels-Alder reaction, except it's wrong. And that's what you're going to do on the test, and it's wrong. Why is it wrong? Notice that this was unsymmetrical and this was unsymmetrical. Whoops, sorry. Let me redraw it then. Do you agree the other possibility, and all I'm going to do is flip the other one over. And I have to remind myself to do that anytime both of them are unsymmetrical. And I think you can easily see that this product looks like this. Notice the two groups are 1, 2, 3, and 1, 2, 3, 4. So this is the correct answer. So on the test, make sure you do that. It won't always be that both of them are unsymmetrical, but you always have to ask that. Now let's go to page 6. Here's the other way this question can be worded. Give me the products, give me the reactants that give me this product. Now, this product is different than all the other Diels-Alder reactions we've looked at. What's different about this product? It's got 2 double bonds in it. Now, when you have 2 double bonds in the product, where did the second double bond come from? The second double bond came from, instead of having an alkene, you had an alkyne. Okay? Now that could possibly happen on the test. So when you have that, watch what I'm going to do. I'm going to initially let this be my diene and that be my dienophile. So notice if I do that, what am I going to do? I'm going to move my electrons back around. Okay, and then this pair of electrons comes down here. So notice I have that and I have that. Now, be careful. Since this is an alkyne, it doesn't matter where you put that, because there's no front and back. But on this carbon, does the OCH3 come in or go out? And that's where we use that rule. Remember, the ones that are in are coming out towards you. The ones that are out are going back. So I know the OCH3 was here. Notice the CH3 is coming out towards you, which means it was here. And since this is an H, that's one of my choices. My other choice, though, and you have to go through both of these choices whenever you have 2 double bonds in the product, was to make these 4 my diene. And just because I've always written them from left to right doesn't, I could have turned this product around. Now notice what that gives me. Now I have this. Notice that's my piece there. And then I'm going to turn this one around like this. Again, my OCH3 has to be out. Okay, actually it's in the plane of the, starting here, but it goes out in the plane. My CH3 again goes in like this. And notice this one is back here. Now, both of these theoretically would give you that same product. Notice if I just move my electrons around, I'm going to get the same product either way. The question is the top method better or the bottom method? So whenever you're trying to predict which method works best, you ask yourself, in this case, are my electron donating groups on my diene and my electron withdrawing groups on my dienophile? The answer is yes. But notice in this case, the diene contains both electron donating groups and electron withdrawing groups. So this is not a good Diels-Alder reaction. So if you had put this on the test, you would not have gotten full credit. Now, this is by far the harder thing to do. It's easy to predict the product given the reactants. but it's a lot harder to predict the reactants given the products. Okay? That's all there is to Diels-Alder reactions. Make sure you work all the homeworks in the textbook on them, and you should do very, very well when it comes to Diels-Alder reactions.